Hey everybody, Trey here. Welcome back to another video. Today we're going to talk about a phenomenon that is often overlooked in the severe weather forecasting process, but can actually provide some very photogenic opportunities for storm chasers and spotters, and that is the landspout tornado. In this video, we're going to talk about what a landspout tornado is, how they form, and give you some tips and parameters that you can look for to determine enhanced areas of landspout tornado potential, and also go over some real-world examples of landspout tornado environments. So let's go ahead and get started. First, let's define what a landspout tornado is. Most tornadoes, and especially the vast majority of your strong to violent tornadoes, are spawned by thunderstorms with a rotating updraft, i.e. supercells. So the thunderstorm, a supercell, has a rotating updraft or mesocyclone, and the dynamics at play with that mesocyclone help to give birth to the tornado. You can see, for example, here, this is a classic picture from Howie Bluestein of the Spearman, Texas tornadic supercell in 1990. You can see the tornado here clearly associated with a rotating thunderstorm. Supercell, you can see the rotation here in that just by looking at the photo. This would be a mesocyclonic tornado. Landspout tornadoes, on the other hand, are not associated with a rotating thunderstorm, i.e. a supercell. They can happen under the base of a developing thunderstorm. They can even happen underneath a fair weather cumulus cloud. They can also happen with supercells, but the supercell dynamics are not going to give birth to the landspout tornado. It will not be associated with the mesocyclone or rotating updraft of a supercell thunderstorm. Now, let's elaborate on that by going into how landspout tornadoes form. All you need for a landspout tornado is a small pre-existing area of spin at the surface and an updraft co-located with that area of spin. Now let's look at some figures from some journal articles to help us decipher what that means. This is figure 20 from Wakimoto and Wilson, 1989. This was really the foundational paper on landspout or non-supercell tornadoes. I'm going to put a link to this paper and any other papers I mention in the description box below so you can do some research for yourself. But again, this was figure 20 from Wakimoto and Wilson, 1989. This is basically a schematic diagram showing the stages of landspout tornado development from left to right. We'll start over here on the left. The vast majority of, if not all, landspout tornado cases are involved with some sort of surface wind shift boundary, whether that's a stalled outflow boundary, a slow-moving front, a terrain-induced convergence zone. Doesn't matter, but most, if not all, landspout tornado cases are involved with some sort of surface wind shift boundary. Now, as you might imagine, the air masses on both sides of that boundary are not homogeneous. In other words, there are going to be inconsistencies in the flow on both sides of that boundary. That creates very small areas of wind shear that form these little eddies or small-scale circulations known as mesovortices. Now, you may have heard of a mesovortex or a mesocyclone. The prefixes meso and meso were used early on by Dr. Ted Fujita to classify these vortices based on their scale or size. A mesovortex is basically a vortex on the storm scale, so you can think of it as perhaps a bookend vortex in a squall line that is a somewhat large area of rotation that can develop tornadic winds. And a mesovortex is a vortex but on a much smaller scale. So these mesovortices are on a very small scale. And these mesovortices in this figure are denoted by these little curled arrows here labeled with letters. And the surface boundary is denoted by this black line along which the mesovortices are situated. Now, what also happens along a wind shift boundary is that you have air that's blowing towards each other, as denoted by the arrows in the schematic diagram here. When you have air that's blowing towards each other, you have convergence along that boundary. When you have convergence, that air is forced to rise. And when you have the ingredients in place that are favorable for convection, moisture, etc., you'll get these updrafts, these convective updrafts, to form along the boundary. And when you have an updraft that moves over a small-scale circulation along the boundary, that updraft acts as a vacuum, so to speak. It takes that vortex along the boundary and stretches it into the vertical, so much so that it connects with the cloud base. And when you have that connection with the cloud base, you then have a landspout tornado. So you can see that it has nothing to do with supercell rotation, a mesocyclone, supercell dynamics. All you need is a pre-existing small vortex or eddy along the boundary and an updraft co-located with that vortex to stretch that little area of spin into the vertical to the cloud base, and then you have a landspout tornado. Here's another figure, this one from Brady and Zoki, 1989. that shows a very similar thing to what the Wakimoto figure showed, but this is as if we were looking at standing at the surface, looking toward an outflow boundary and new convective development. So you have two air masses converging here, right along the boundary between the two. These little vortices develop, these mesovortices there, and the convergence along the boundary forces that air to rise into the vertical, and you get new convective development, which can then stretch that circulation into the vertical. And when you have this rapid convective development, it can stretch it so much that it connects with the cloud base, and you have a landspout tornado. Now, just a couple of notes about landspouts. You have to have the connection with the cloud base in order for a vortex to be determined to be a landspout. If you just see a little dust whirl underneath a cloud base, but you don't have that connection with the cloud base, you can't definitively say that's a landspout. Usually, you will see a nub-type funnel right at cloud base, with that dust tube extending all the way to the ground, maybe toward a debris cloud at the surface, or sometimes you'll see the full dust tube extending all the way up very close to the cloud base, at which point you know you have a landspout tornado. But again, you have to have that connection with the cloud base in order for a vortex to be termed a landspout. Also, oftentimes I hear more inexperienced agencies, people who aren't usually accustomed to seeing landspouts, say things like, oh, this was a landspout, it was not a tornado. That statement is categorically false. A landspout is a type of tornado. Now, if you're a storm chaser and you decide not to count landspouts as part of your storm chasing statistics, that's your prerogative. But a landspout is a type of tornado, and there should not be a differentiation between a landspout and a tornado because they are one and the same. So how can we forecast landspout tornadoes? As we said, these can be very difficult to forecast because of their very random nature in general, and oftentimes they'll result from a boundary that maybe models can't resolve days ahead of time, or the overall conditions will come together very quickly before a landspout event occurs. But there are some things that you can look for, generally on the morning of an event or while you're actively out chasing, to help determine areas of enhanced landspout potential. As we said, most, if not all, landspout events involve some sort of surface wind shift boundary. And we said that can be anything from a stalled outflow boundary, a slow-moving frontal zone, even a terrain-induced convergence zone. For example, if you may have heard that the Denver metro area, Denver, Colorado metro area, has a heightened frequency of tornadoes, especially in the late spring and summer months. And that is because of something called the Denver Convergence Vorticity Zone, or DCVZ. And what happens is when you have southeasterly flow going up and over the Palmer Ridge, which is this higher terrain feature there in east central Colorado, you have southeasterly flow going up and over the ridge. That meets with downslope flow off of in the foothills of the Rocky Mountains, creating some sort of boundary, wind shift boundary, that sets up right in or near the Denver metro area. And that DCVZ boundary, as the name suggests, is a source of convergence and low-level vorticity or spin from which landspouts can form. And that's why you see every year, usually every year, pictures coming out of the Denver airport or somewhere around the Denver metro area showing these beautiful landspout tornadoes. Usually they're caused by the Denver Convergence Vorticity Zone. I have a few papers that I found on the DCVZ. I'll put the links to those in the description below. Now, the main thing to watch for with these boundaries in landspout cases is that they either need to be stalled or very slow moving. And the reason is because if you have updrafts going up along a fast moving or surging boundary, those updrafts are going to initially go up along the boundary, but very quickly they will become very much displaced from the boundary and that source of vorticity that exists along the boundary, and therefore you will have a very short, perhaps non-existent window for any updrafts to coincide with those areas of spin along the boundary, as the boundary will be surging away from those updrafts. So you would much rather have a stalled boundary where you have updrafts going up along that boundary. Therefore, you'll have a much longer window for those updrafts, a much better chance, much longer window for those updrafts to coincide or become co-located with areas of spin along the boundary and therefore produce landspouts. So it is very key that your surface boundary that is in play needs to be very slow moving or most favorably stalled out. Now you have your boundary in place. We also need spin along that boundary, scientifically known as vorticity, those mesovortices we talked about. Now, it is a little bit difficult to measure vorticity at this small of a scale. We don't have a product that directly measures these mesovortices, the vorticity on this small of a scale, but there is a product that we can use on the SBC mesoanalysis page that we'll talk about in just a second that we can use as a proxy for measuring spin along the boundary. Sometimes you can look at the radar and see these boundaries and the vorticity along these boundaries pretty clearly. This is an example of the DCVZ back from 1998. Clearly, you can see it on reflectivity here, and you can also see on velocity little areas of spin along the boundary, these little, very weak-looking tornadic type couplets. Obviously not tornado strength, but these are indications of small areas of vorticity, these mesovortices along the boundary. These reds are moving away from the radar, which is located right here. Green's moving toward the radar, so you have a convergence boundary right along here, and you can easily pick out these little tiny weak couplets along the boundary. Those are your mesovortices. So sometimes you can spot them visually on radar, but we also do have a product on the SBC mesoanalysis page that we'll talk about in a second that can act as a proxy for measuring the vorticity or spin along a surface boundary. Now, the next parameter you want to look for when forecasting landspout tornadoes is one that we've talked about ad nauseum on the channel here. We've even given it its own video detailing how important it is in aiding that stretching process of stretching low-level spin into the vertical to aid in supercell tornadogenesis, and that, of course, is 0 to 3 kilometer CAPE, otherwise known as 3 CAPE. And as we talked about before, 3 CAPE is super important in supercell tornadogenesis, but because that stretching process, that stretching of the low-level spin into the vertical, is basically the lifeblood of landspout tornadogenesis, as you might imagine, 3 CAPE is an extremely important product to look for when forecasting for landspout tornadoes. Just as a refresher, 0 to 3 kilometer CAPE is exactly as it sounds. It's a measure of instability in the lowest 3 kilometers of the atmosphere. So it is basically a measure of the ability of air parcels to rise on their own in that lowest 3 kilometers of the atmosphere. Strong low-level instability, i.e. high 3 CAPE, allows air parcels to rise very efficiently in the low levels of the atmosphere. And that can really enhance that process of stretching any low-level vorticity or spin into the vertical in both supercell tornado environments and especially landspout tornado environments. So 3 CAPE is very, very critical in forecasting landspout tornadoes. Generally, anything above about 50 joules per kilogram is considered adequate. And in a lot of cases, in most cases, you'll see that 3 CAPE value much higher. And the higher the 3 CAPE, the better. You'll often see in landspout environments that 3 CAPE value soar well into the triple digits. Now, those two parameters, surface vorticity, usually located along a boundary, and low-level instability are critical in landspout tornado forecasting. You want to see an overlap between strong spin at the surface, i.e. strong surface vorticity, and strong low-level instability, i.e. high 3 CAPE. And the fine folks at the SBC have a parameter that allows us to see surface vorticity and 3 CAPE on the same map. If you go to their mesoanalysis page and you scroll all the way over to the multi-parameter fields tab, go down to the one that says surface vorticity and surface 3 kilometer CAPE. This is the holy grail product for landspout tornado forecasting. This shows us surface vorticity, which is denoted by the blue contours here, and 0 to 3 kilometer CAPE, which is denoted by the red contours here. So again, you want to look for areas where you have strong 3 CAPE overlapping strong surface vorticity. So for example, if you look down here in the corner of the map, and I'm doing this at present time, this is not any particular landspout case. This is just happens to be what this product is showing at the time I'm recording this. So for example, if we were looking for landspouts, we might look in this area. Obviously, this is out in the Atlantic Ocean, but just for the sake of example, we'll look over here. You see we have some contours there of surface vorticity, those blue contours there, that lie underneath these red contours here for 0 to 3 kilometer CAPE. We're seeing strong surface vorticity beneath about 100 to 125 joules per kilogram of 3 CAPE. That is a favorable environment for landspout tornadoes, assuming the other ingredients are there. You have a boundary, and you have some of the other ingredients we'll talk about in just a second. But this, again, is the holy grail product for landspout tornado forecasting, and this is very, very helpful. I always check this very frequently when I'm out chasing, both for supercell events and for landspout events, because when you're looking along a boundary and you see strong surface vorticity and strong low-level instability co-located with that vorticity, that is going to show you an enhanced area of landspout tornado potential. Now, just to reiterate, the surface vorticity that is plotted in this product is not a direct measurement of those mesovortices or small-scale vorticity that exists along a boundary that is favorable for landspout tornadoes. This vorticity that's measured here is on a slightly larger scale, but again, it's a pretty good proxy for what vorticity lies along a boundary, so we can use it in conjunction with 0 to 3 kilometer CAPE by using this product to judge enhanced areas of landspout potential. Our next parameter goes hand in hand with strong low-level instability, and that is steep low-level lapse rates. And you can find them on the SPC mesoanalysis page by going over to the thermodynamics tab, all the way down to low-level lapse rates. A lapse rate is simply the rate of change of temperature as you go up through a layer of the atmosphere. And we're specifically keying in on the low levels of the atmosphere here, which in this case is the 0 to 3 kilometer layer from the surface up to 3 kilometers. When you have steeper low-level lapse rates, that allows air parcels to rise really rapidly in the atmosphere, and that can help twofold in landspout tornadogenesis. Number one, just like strong low-level instability or 3 CAPE, that can really help aid in that stretching of vorticity into the vertical, and it can also create more robust convective updrafts. As we know, we need convective updrafts to be co-located with that vorticity at the surface to help stretch that into the vertical. Well, if you have stronger, steeper low-level lapse rates, that means that air is rising more rapidly. That leads to more robust updrafts, and therefore stronger updrafts can lead to better landspout potential. So we want to see those landspout or those low-level lapse rates generally on the steeper side. Generally, anything above 6 degrees Celsius per kilometer is considered adequate. That means your temperature for every kilometer you go up in the atmosphere in that 0 to 3 kilometer layer is decreasing by 6 degrees Celsius. Now, anything above 6 degrees Celsius per kilometer is considered adequate, although in most landspout cases you'll see that much higher, in the 7, 8, 9, 10 degrees Celsius per kilometer range. That indicates that you have much steeper lapse rates, much more drastic temperature change in the low levels of the atmosphere as you go up, and that yields more robust updrafts and can help out in that stretching potential of that vorticity into the vertical. You also want to see some deep layer instability to support robust convection. And you can find all of your instability metrics, again, under the thermodynamics tab here on the mesoanalysis page. The 100 millibar mixed layer CAPE is the one that you should be using most often. I did a whole video previously on why mixed layer CAPE is more accurate than surface-based CAPE in a lot of scenarios. I'll put that in the description box below. But again, you want to see some deep layer instability through the entire atmosphere to help support robust convection. We want that strong low-level instability to be able to aid in the stretching process, but we want to see some instability throughout the entire atmosphere to help sustain robust convection. Now, this is not as critical as some of the previous parameters we've looked at. There have been plenty of landspout cases where we've seen very minimal deep layer instability, but generally something about 500 to 1,000 joules per kilogram is considered adequate, and oftentimes you'll see even more than that, 1,500, 2,000, 2,500 joules per kilogram of mixed layer CAPE, which supports robust convection. Obviously, the higher that CAPE value is, the higher the instability is in the atmosphere, and the more robust convection you'll be able to sustain. So in most landspout environments, you will see a decent amount of instability in the deep layer via mixed layer CAPE, but they can occur in lower CAPE environments. What is critical is having minimal convective inhibition, or SIN, and that's just a fancy word for the cap. And the cap, as we know, acts as a lid on the atmosphere. It can suppress robust convection and allow storms to remain elevated in particular environments. So you can think of it, again, as a lid on the atmosphere. If you have this lid in place and you have a boundary with surface vorticity along it, and you have an updraft going up over that boundary, if you have a lot of convective inhibition in place or a lot of capping in place, that's going to act as a wall between these two. That surface vorticity will not be able to be stretched into the vertical underneath that updraft because there's that barrier in the way. If you don't have that barrier in the way, i.e. you have minimal convective inhibition, then you'll be able to easily stretch that into the vertical, assuming the other parameters are there, and much more easily obtain landspout tornadoes. So you want to see decent ML CAPE, or instability, in the deep layer, and you also want to have little to no convective inhibition or capping in the environment. The closer to 0 that SIN number is, the better. Now on this plot, the mixed layer CAPE plot from the SPC mesoanalysis page, these red contours are your CAPE contours, and this blue shading is your convective inhibition. So again, you want to see at least decent instability in the deep layer, decent ML CAPE, and you also want to see minimal convective inhibition, because that, if you have more capping, that will block that connection between the updraft and that surface vorticity, and you'll have a much harder time attaining landspouts in that environment. The last thing you can look for when forecasting landspout tornadoes is deep layer shear. And you can find the wind shear parameters on the SPC mesoanalysis page under the wind shear tab. You can use something like 0 to 6 kilometer bulk shear. Now, for typical landspout tornado environments, you generally have weaker deep layer shear. And the reason is very similar to what we talked about with the fast-moving boundary. If you have strong deep layer shear in an environment, that usually means you have stronger flow aloft. that will steer the storms or push the storms off of the boundary. So any updrafts that go up along the boundary are going to be steered off of the boundary pretty quickly when you have stronger winds aloft, stronger deep layer shear, and therefore those updrafts will quickly become disconnected from that source of vorticity along the boundary, and you'll have a much decreased chance for landspouts from those updrafts. If you have a more weakly sheared environment, those updrafts are going to go up on the boundary, but they will stay very close to the boundary for a longer period of time because you don't have as strong a flow aloft to push those updrafts out of the zone of ascent along the boundary. Therefore, you'll have a much longer duration, a much better chance for those updrafts to stay near the boundary and interact with that vorticity along the boundary to produce landspouts. Now we can talk about the orientation of the flow of the storm motion vectors, of the shear vectors with respect to the boundary. If you have storm motion vectors that are along the boundary or parallel to the boundary, that can keep those updrafts in that zone of ascent along the boundary for longer. But then you start getting into the idea of you may have a lot of updrafts going up at once and conglomerating and potentially producing a decrease in landspout potential. But when you have isolated updrafts in general and you have a more weakly sheared environment, those updrafts are going to stay in closer proximity to that boundary for longer. Therefore, you'll have a longer duration and greater chance for landspouts along that boundary. Now, this is not absolutely critical. I've seen plenty of landspout events occur in more strongly sheared environments or supercell environments, but generally, your more robust, longer-lived landspouts are going to come from more weakly sheared environments. Now, just like what we have for supercells and significant tornadoes, there are a couple of composite parameters that we can use to help identify areas of enhanced landspout tornado potential. And so if you go on the SBC Mesoanalysis page and scroll over to the Composite Indices tab, you go down to the non-supercell tornado parameter. And I'll zoom in here so you can see a little bit better what's going on right now. This is the current map as we're recording this. And the non-supercell tornado parameter was developed several years ago. Here's the main paper on the NST parameter by Baumgart and Cook 2006, and you'll see over here that is the equation used to calculate the non-supercell tornado parameter. So it basically takes into account all of the different products and variables that we talked about earlier. So it's just a product of low-level lapse rates, in specifically the 0 to 1 kilometer lapse rates, 0 to 3 kilometer CAPE, mixed layer sin, and you'll see that it's 225 minus mixed layer sin, so the less the mixed layer sin is, the greater the non-supercell tornado parameter will be. Same thing for deep layer shear. They use the 0 to 6 kilometer shear, and that is 18 minus 0 to 6 kilometer shear. So same thing, if the 0 to 6 kilometer shear is weaker, the non-supercell tornado parameter will be greater. And then finally, surface relative vorticity. It's just a product of those 5 parameters, and you'll notice all these divisors as well, divided by 9, divided by 100, etc., etc. That just normalizes this value. Basically, it just is a way to help us get more usable, more workable outputs from the non-supercell tornado parameter so that we're not dealing with a bunch of different, super long decimal places, etc., etc. So anything greater than 1, if the non-supercell tornado parameter is greater than 1, that is an area that could potentially harbor more possibility for landspout tornadoes than surrounding areas. So if we go back to our mesoanalysis page, for example, you see this area right here off the Mississippi-Alabama coast has some 2s and 3s over there. That means that the non-supercell tornado parameter is elevated, and that area may be slightly more favorable for landspout tornadoes than areas elsewhere. Same thing, for example, here off the South Carolina coast, value of 2 right in there. Exact same thing, a little bit enhanced potential for landspout or non-supercell tornadoes. There's also another parameter that we can take a look at. If you go back to the Composite Indices tab and go all the way down to enhanced stretching potential. This takes into account those variables that really modulate the stretching of that vorticity at the surface into the vertical. So this was developed by Caruso and Davies, 2005. And this parameter basically just takes into account 2 of the main variables that modulate that stretching potential. So here's the equation for it. It's basically a product of the 0 to 3 kilometer CAPE and the 0 to 3 kilometer lapse rates. And of course, we're normalizing it to get rid of those units and make the values a little bit more workable. So again, as we talked about, the 0 to 3 kilometer CAPE or 3 CAPE and those low-level lapse rates really modulate how efficiently any spin at the surface is going to be stretched by those updrafts into the vertical. So when the enhanced stretching potential is higher, generally again greater than 1, that means you have areas where that stretching potential is going to be much more maximized versus areas that are less than 1. And you'll see here that it says that enhanced stretching potential is set to 0 when the 0 to 3 kilometer lapse rate is less than 7. So basically their threshold for those low-level lapse rates is 7 degrees Celsius per kilometer. As we said, anything greater than 6 degrees Celsius per kilometer for those low-level lapse rates is adequate, but usually in most landspout events we see that 7, 8, 9 degrees Celsius per kilometer value to really mean that those low-level lapse rates are strong. And also, if total mixed layer CAPE is less than 250 joules per kilogram, the ESP, enhanced stretching potential parameter, is set to 0 as well. So again, you need a little bit, at least a little bit, a decent amount of that deep layer instability to foster those more robust updrafts. So for example here, we'll take a look in southeast Louisiana. Enhanced stretching potential is maximized right there near the New Orleans area, 4s and 5s right in there. And if we were to look at our low-level lapse rates, you'll see that those are maximized there, 7, 7.5 right in that area, as well as our 0 to 3 kilometer CAPE, also maximized 100, 150, 175 joules per kilogram right in that area, and therefore we have some enhanced stretching potential in that southeast Louisiana area. Now, as we've talked about with composite parameters before, they don't tell us the whole story. They don't take into account the nuances of the environment. It's simply an equation that spits out some numbers, and it does not take into account the nuances of the environment. For example, you can have all those parameters of the non-supercell tornado parameter maxed out. But if you have a boundary that is surging pretty fast, you're going to have that landspout potential much decreased because of that the much shorter residence time of those updrafts on the boundary. So again, just like with the supercell composite and significant tornado parameters, take them with a grain of salt. It's best to look at a holistic view of the environment, take a look at each of the variables individually and the nuances of the environment to come up with a forecast yourself, rather than relying on just these numbers output by these composite parameters. But these composite parameters do help us at least identify areas where there may be a little bit of enhanced potential for non-supercell or landspout tornadoes. All right, let's take a look at some real-world examples. We'll take a look at a few cases where landspout tornadoes occurred and see if we can check all the boxes as far as our different variables go. Now, for each case, we'll do a very quick look at the upper air pattern and the surface pattern, and then we'll take a look at each of the different variables that we discussed earlier on in the video to see if we can decipher why landspouts occurred in that given area. The first case we're going to look into is a landspout tornado that occurred near the town of Tappen, North Dakota on May 19th, 2021. This was a very photogenic landspout, as you can see from a local resident's photos here. Very beautiful landspout. Even had that little nub funnel at cloud base with a dirt column that extended all the way up almost to the cloud base, and even had an interior funnel there for some time. So just a very beautiful, pretty textbook landspout near the town of Tappen, North Dakota. And this occurred on a day where severe weather was not really expected for the northern plains. They did eventually add a marginal risk for that central to eastern North Dakota corridor by the midday outlook, but it was mainly for damaging winds. There was not any tornadic activity expected. Let's look at our 500 millibar map to start off, and you'll see not much going on across the northern plains. There is this trough, pretty big trough centered across the Pacific Northwest, strong flow rounding the base of that trough, but not much going on across the northern plains, and this trough really didn't make any eastward progress throughout the day. You'll see that winds aloft here at 500 millibars actually decreased somewhat going into the late afternoon, early evening. We start out with about 20, 25 knots of flow, decreasing to about 10, 15, maybe 20 knots of flow there across central North Dakota by early evening on the 19th. Surface pattern, pretty quiescent surface pattern, but we did have a surface boundary to deal with. Weak frontal zone making its way through North Dakota here. You see the kinks in the isobars there across southern Canada. And clear wind shift at the surface. We'll take a closer look at this here in a second, but definitely a weak cold front that was making its way through western North Dakota on the morning of the 19th. This boundary was moving somewhat, and I'll animate the picture here. You'll see by late afternoon or so, that boundary was still, it had moved, but not quite all that much. We see the wind shift here somewhere in this vicinity, especially southern portions of the boundary had moved a little bit more slowly, perhaps than the northern portions of the boundary. So the boundary was definitely moving, but not all that fast to nix landspout potential along it. Here's a closer look at the surface map. This is at 21Z on May 19th, 2021, just before the tornado occurred near Tappen. Occurred just after 4:30 p.m. Central Daylight Time. But you'll see here clearly a wind shift along that frontal zone right in this vicinity here. We see winds on the west side of the boundary out of the north, more southerly winds on the east side of the boundary. So a clear wind shift there. And the slow moving front provided the source of convergence and vorticity at the surface to aid in landspout formation along it. Let's go through our checklist of ingredients. We'll start off with 0 to 3 kilometer cape and surface vorticity. You can see a lot of surface vorticity already pooled along that frontal zone on the morning of May 19th. This is at 12 Z, and as we go through the afternoon, that maintains itself. And we also build a nice pool of low-level instability along the boundary, about 75 to 100 joules per kilogram of 0 to 3 kilometer cape, co-located with that spin/vorticity along the boundary. So that is always a plus for landspout tornadoes. Low-level lapse rates also on the high side as well. We really started to build in those lapse rates by mid to late afternoon, 8 to 9 degrees Celsius right along that boundary in south-central North Dakota. So the stretching potential in this environment was very, very high. You had very strong low-level instability and strong low-level lapse rates to really help those updrafts stretch the low-level spin into the vertical. Mixed layer cape in the deep layer also was adequate. Nothing astronomical here. You'll see about 1,000 joules per kilogram of mixed layer cape by 21Z, 4 p.m. Nothing, again, astronomical, but definitely more than adequate for landspouts. And we also see a lack of convective inhibition here across south-central North Dakota. A little bit of that blue shading up to the north, but in our area of interest near Tappen, not much convective inhibition to speak of. As far as deep layer shear goes as well, we'll look at our 0 to 6 kilometer shear vectors, and as a result of that trough not really moving out of the Pacific Northwest and our flow aloft weakening a little bit going into the afternoon, our deep layer shear was pretty much sub 30 knots here across south-central North Dakota, meaning that those updrafts would stay along that boundary much longer, much more residence time, and much more time for landspouts to occur on the surface boundary. Here is a RAP model proximity sounding from Jamestown, North Dakota, so just east of Tappen, at 4 p.m. Central Daylight Time, 21Z on May 19th, 2021. Adequate instability, you see here up through the column, about 1,000 joules per kilogram of mixed layer cape, and very weak deep layer shear. The portion of the hodograph that represents that area under 6 kilometers, the red and green portions, you can see that that is very, very tiny. 0 to 6 kilometer shear only registering at 7 knots, so very, very weak deep layer shear environment. Both very favorable, that adequate cape and that weak deep layer shear for landspout tornadoes. Now you will see that this sounding does not register a lot of 0 to 3 kilometer cape, only 32 joules per kilogram of 3 cape in this particular sounding. I think that's just an artifact of the cloud bases being quite high. The LCL almost up to about 3 kilometers or so. So you're not going to get a lot of that hodograph where the instability is located to be below that 3 kilometer threshold. And again, this is a model sounding, so it may be undersampling things compared to what mesoanalysis was showing, about 75 to 100 joules per kilogram of 3 cape. But nonetheless, our low-level lapse rates very, very strong. 0 to 3 kilometer lapse rate approaching 10 degrees Celsius per kilometer. That is extremely, extremely steep. Lots of surface heating, allowing those temperatures in the low levels to warm uninhibited. Very well-mixed boundary layer, very, very steep lapse rates in the low levels, helping to really enhance that stretching ability of those updrafts in this environment. Looking at some radar data here, you see we had quite a few updrafts going up along the boundary throughout the afternoon. We start about 20Z, 3 p.m. or so. We get some more robust updrafts to form near Tappen, and then eventually a very robust updraft there that looks like it's propagating along the boundary. You'll see it fires there along I-94, then just kind of moves to the southwest along that surface boundary. At this point, the landspout was ongoing, very robust updraft there near Tappen. You won't see much on velocity data here. You'll notice that storm near Tappen does try to develop a couplet here. This is just before tornado genesis. Little bit of a couplet there, perhaps. Very hard to see, but there's something right in there. Dissipates the next scan, so difficult to tell if this was associated with the landspout or not. Oftentimes you won't see a robust signature on radar from a landspout tornado. The reason is because they don't extend well up into the storm like a supercell tornado does, which is connected to the rotating updraft or mesocyclone over supercell. These are just, landspouts are just spin, stretched up to the cloud base by the updraft, and that's it. So they're very shallow circulations, and you really have to be very close to the radar site to be able to see them efficiently. They are oftentimes also a lot weaker than supercellular tornadoes, so again, they can be very difficult to see on the radar from both a velocity and a reflectivity perspective. All right, let's move on to our next case. If you've ever heard of the storm chaser and photographer Jim Reed, and you've seen his book, this is kind of the famous photo on the cover of that book, him running up very close to the tornado. Here's a wider view. This was a very photogenic landspout that occurred near Selkirk, Kansas, in far western Kansas, on May 8th, 2008. And this actually occurred on a day that was on which supercells were favored. There was stronger deep layer shear on this day. And as we've talked about, weak deep layer shear is not a prerequisite for landspouts. It does help you get longer lived landspouts, but this just goes to show that you can get photogenic, longer lived landspouts even when deep layer shear is on the stronger side. We'll talk about the deep layer shear here in just a second. Well, the cause of that deep layer shear was a nice shortwave trough moving into the central high plains by the afternoon hours on May 8th. You can see right here a very low amplitude feature, but a nice shortwave trough, well-defined shortwave moving in, strong belt of flow rounding the base of that trough. Introducing some nice stronger westerly flow aloft across the region. At the surface, we had, as a result, some very nice surface cyclogenesis to deal with. As you see in the morning there, broad surface cyclone that really tightened itself throughout the afternoon hours. By mid-afternoon, we had a nice 998 millibar surface low, nice tight 998 millibar surface low there in southeast Colorado. That helped to back those surface winds to help that increase that deep layer wind shear for supercells, but it also helped increase the surface vorticity out ahead of it on the northeast side, which you'll see here in just a second. Taking a look at our actual surface data here from 20Z, 3 p.m. Central Daylight Time, 2 p.m. Mountain Standard Time on May 8th, 2008. We can pick out a couple of different features. You first off can denote this surface low here across the Kansas-Colorado border area. A little tough to tell because we have a scarcity of surface observations in this region, but you can see the nice counterclockwise flow around that low center situated somewhere here on the Kansas-Colorado border vicinity there. We also have a dry line to speak of, dew points in the teens, 20s, and 30s, and into the low 40s out here to the west. Dew points in the mid-50s here across the southwest Kansas and into the Texas and Oklahoma Panhandle vicinity. So our dry line situated somewhere in here. Nice slow-moving to stationary boundary here to focus our surface vorticity. Also, the surface low helps to increase the surface vorticity out ahead of it. You can see those winds shifting from southerly to pretty much easterly here across northwest Kansas. That creates that spin at the surface that helps to increase that surface vorticity product. And if we actually look at our 0 to 3 kilometer cape and surface vorticity, you will see that surface vorticity starts to really build into western Kansas by mid-afternoon. A nice plume of 0 to 3 kilometer cape as well. Nothing off the charts, but about 50 knots or 50 joules per kilogram or so, coinciding with that low-level vorticity there. Again, that is our cheat code for landspout tornadoes. Our low-level lapse rates also started to build in throughout the afternoon. You see that plume of those orange colors there working their way into western Kansas. That is 8 degrees Celsius per kilometer and higher, so 8, 9, even 10 degrees Celsius per kilometer here in southeast Colorado. So very steep low-level lapse rates as we'd had unimpeded surface heating throughout much of the day across western Kansas, helping to really bolster those low-level lapse rates. Deep layer instability, also adequate for landspout tornadoes here. You see through the afternoon, we have that nice plume of about 1,000 joules per kilogram of mixed layer cape. A little bit of that blue shading, indicative of convective inhibition remaining. But as you'll see on our proximity sounding we'll show in just a second, there really wasn't much left to really impede landspout tornado formation. It was pretty much negligible by this point. So nice deep layer instability, more than adequate for landspouts. Lower convective inhibition helped to get those updrafts to be more robust. Now, deep layer shear, as we talked about, was on the higher side for this event, at least for typical landspout tornado events. So if we look here at our 0 to 6 kilometer shear vectors, you will notice about 40 knots or so out across western Kansas, 40 to 50 knots or so. That, as we talked about, does tend to allow updrafts to get pushed away from the boundary a little bit, and you'll actually see another shot from Jim Reed of this tornado. You see those updrafts here in the background, and that landspout is well out behind those updrafts. Those updrafts were moving well away from this tornado, and the tornado was anchored onto whatever source of surface vorticity it was, whether it's the dry line, whether it's that low-level vorticity from the surface low, trying to anchor to that boundary, that source of vorticity, while the updrafts are moving off of it thanks to that stronger upper-level flow and deep layer shear. So, but that, again, it doesn't mean you're not going to get longer-lived landspouts. It just means you might get a very nice tilted, ropey landspout like this that may not last as long, but still can be very photogenic, and in this case, it certainly was. Now, here is our proximity sounding. This is from a John Davies article on this Selkirk, Kansas tornado case. And this has been a little bit modified using the lower level profiles, the surface observations near Selkirk, Kansas. We do see nice instability there, mixed layer cape of about 1,200 joules per kilogram. Deep layer shear on the higher side, definitely in the margin, definitely favorable for supercells, about 40 knots or so. But again, not a prerequisite for Landspout tornadoes. You will see that 0 to 3 kilometer cape about 64. Nothing nothing extraordinary, but definitely more than adequate for Landspouts here. And those nice steep low-level lapse rates approaching 8.5 to 9 degrees Celsius per kilometer. Definitely favorable for Landspouts, and we certainly got a nice Landspout tornado out of this case. Here's some radar data from this case. You'll see the storm start to fire between Tribune and Leota, Kansas, and this is about when the Landspout was occurring. Again, you see not a mature supercell by any means. It doesn't take a lot. All it takes is a little spin at the surface and an updraft co-located with that spin to have a Landspout tornado. Eventually they would become stronger. But you can actually see the dry line boundary here on radar, and those storms moved well away from the boundary thanks to that stronger upper level flow. So in that early stages of storm development there, while storms were very close to that boundary, that is when the Landspout tornado occurred, and then they eventually moved off. The Landspout tried to hang on, taking on that ropey appearance well behind these updrafts, but eventually that deep layer shear allowed the connection to be broken between the updraft and the circulation at the ground. And finally, just some velocity data to show you that, once again, Landspouts are very difficult to dissect on radar. If we zoom in here to our Selkirk area, you won't see a very strong couplet at all, indicative of any tornadic activity. Once again, Landspouts are quite shallow. They extend from the ground up to basically the cloud base, and that's about it. So unless you're very close to the radar, unlike we are here, it's very difficult to depict Landspouts on velocity data. For our final case, let's head west into Arizona. Yes, Arizona can get some interesting weather from time to time, including some occasional tornado events. And this was taken on October 21st, 2018 by storm chaser Jeremy Perez near the old Indian ruins site called Two Guns, about halfway between Flagstaff and Winslow on I-40 in northern Arizona. Just an absolutely beautiful landspout, classic look to it with the funnel up top, dirt column extending up from the ground. One of the best examples of a landspout I've ever seen coming out of Arizona. Now, there was a marginal risk out for this day, but it was centered a little bit farther south, central into southern Arizona, for mostly hail and wind. And the impetus for this severe threat was a weak but well-defined trough centered across the Southern California coast, allowing some stronger flow to make its way into Arizona. Now, when you have this ambient southwesterly flow, that can trigger something called the Mogollon Rim Convergence Zone. And this is a paper written by David Blanchard, who is a prolific meteorologist, used to be a meteorologist at the National Weather Service in Flagstaff. I'll put the link to this paper, of course, in the description box below. And if you're not familiar with the geography of northern Arizona, there is the Mogollon Rim, which is a higher terrain feature. And on top of that, you have a plateau that houses the Little Colorado River. And inside this river valley, we can get flow that gets channeled up the valley, very similar to the Central Valley in California. That flow gets channeled up into the valley and comes out of the southeast. And when you have ambient southwesterly flow, that allows those winds to converge within the valley, and you get a convergence zone within that river valley called the Mogollon Rim Convergence Zone. And on this day, you could actually see it on radar. Just like the Denver Convergence Vorticity Zone in Colorado sometimes shows up on radar, this one showed up as well. You can see the fine line here. Very well-defined example of the MRCZ in action. And by this time in the early to mid-afternoon, it had already fired some storms. You see a supercellular structure there initiating off of the MRCZ with some additional updrafts to the east. So very interesting setup. This, of course, provides the source of surface vorticity or spin that is needed to support landspout tornadoes. And oftentimes when the MRCZ is going, you'll see a lot of severe weather up in northern Arizona. One of my favorite places to chase back when I lived in Arizona, because the terrain is very flat up there, and you can get some very plains-like views of supercells and landspouts when the MRCZ is active. So going back to our checklist of ingredients, we'll start off with our surface vorticity and 0 to 3 kilometer cape. Definitely low-level instability built throughout the afternoon. About 50 to 75 joules per kilogram of mixed layer cape there, coincident with that MRCZ. Now, you'll notice that we don't have any of those blue contours here coincident with that maximum in low-level cape. That could be because, again, this surface vorticity product from the SPC is on a little bit larger scale than what the surface vorticity is needed for Landspout. So it may not be resolving the vorticity along the Mogollon Rim convergence zone, but I assure you there was definitely some spin along that boundary, coinciding with this low-level instability maximum across northern Arizona. Low-level lapse rates were also very steep as well. We'll take a look here at that. You'll notice by mid-afternoon or so, a nice plume of 8 to 9 degrees Celsius per kilometer lapse rates there up across much of northern Arizona. Strong surface heating allowed those updrafts to be very robust thanks to very strong low-level lapse rates. Deep layer instability, not a thing that Arizona is known for necessarily, but you'll notice on this day that we had plenty of instability in place by 21Z, about 1,000 joules per kilogram of mixed layer CAPE, very minimal convective inhibition as well, where that instability was maximized. Now, deep layer shear was a little bit on the higher side, especially for Arizona standards, but definitely on the margins for supercells. You see there about 30 knots or so across much of northern Arizona. That is a little bit on the low side for robust supercells. You can still get some spinning supercells out of that. And it also can allow a little bit of stronger flow aloft, allowed those updrafts to move off of the boundary. We recall the picture of this, definitely a little bit of tilt to the funnel there. That low-level spin anchored on that boundary, and those updrafts moving a little bit away from that boundary caused that little bit of tilt in the landspout itself, but not enough to prohibit landspout formation. We've said ad nauseum so far that strong deep layer shear isn't always an inhibiting factor for landspouts. And the previous case in Selkirk, Kansas, and this one, definitely good examples of that. Here is a RAP model proximity sounding from Winslow, Arizona at 21Z, so 2 p.m. Mountain Time, right about as the landspout was occurring on October 21st, 2018. Adequate instability, about 800 joules per kilogram of mixed layer CAPE. Low-level lapse rates very strong within that well-mixed boundary layer, 72/43. So very strong lapse rates in the low levels, approaching about 8.5 to 9 degrees Celsius per kilometer. And you see the evidence of the Mogollon Rim convergence zone in action. Those east-southeasterly surface winds going up the valley, converging with those mid and upper level southwesterly winds to create that convergence zone. Again, deep layer shear a little bit on the high side, but still not inhibiting landspout formation. All in all, a very nice thermodynamic profile for landspouts. Here is some radar data from that day. Once again, the MRCZ was in full force, very well defined on reflectivity and velocity for that matter. Supercell had fired off of the MRCZ by early afternoon and translated off to the northeast, remaining close enough proximity to the boundary to still tap into that source of low-level vorticity, and that landspout popped out the backside of that storm. Just a textbook example of how Arizona can get in on the tornado action. When that Mogollon Rim convergence zone fires up, definitely keep an eye on that northern Arizona target, especially when the ingredients for thunderstorms are in place. So that's going to do it for this video. Hopefully you learned something new about landspout tornadoes. Once again, they are very difficult to forecast well ahead of time, but hopefully this video gave you a little bit of a checklist you can use when you're making a forecast or you're out chasing to determine areas of enhanced landspout potential. So with that, thanks for watching, and we'll see you in the next video.